Hello everyone, welcome to my channel. So this is the second part on the miscellaneous exercise on chapter 1 sets. On my previous video, I have discussed the work problems on the questions from 1 to 8, all the solutions for the problems number 1 to 8, and on this video, we'll discuss the work problems based on the question from question number 9 to question number 16 of the chapter 1 sets miscellaneous exercise. Okay, so let's go directly with the first problem, that is the question number 9. Using properties of sets, show that A union A intersection B is equal to A. So let's directly use the distributive law here. A union A intersection A union B. Right? What is A? A union A, that is A, right? Again, intersection A union B. If you take the A union B intersection A, you will get the same set A itself. I hope it's clear. Now on to the second problem. A intersection A union B is equal to A. Again, let's prove it through distributive law. A intersection A union A intersection B. Right? A intersection A is what? Again, A itself. Union A intersection B, A itself, right? A union A intersection B will give you the set A itself. Hence we have proved both using the distributive law. Now let's discuss the 10th problem. Show that A intersection B is equal to A intersection C need not imply B is equal to C. So that is, if A intersection B is equal to A intersection B, it doesn't implies that B is equal to C. That is, B and C can be separate sets and they don't have to be equal sets. Let's take an example. So let's say A is equal to 0, 1 and B is equal to 0, 2, 3 and C is equal to 0, 4 and 5. So let's take the A intersection B here. What is A intersection B here? It is 0, right? The element 0 is the common element, and A intersection C, again what it is? 0. Now we have the condition same as that is A intersection B is equal to A intersection C. Now we have to prove that it does not imply that B should be equal to C. So we should find an example such that where B is not equal to C. Such that one example is what we have written over here. Okay, now let's take B and C. Here you can see that the element 2 does not belongs to C, right? Again, the element 5 does not belongs to B, and hence here you have B is not equal to C. I hope it's clear. It's very easy. You can just take some random examples and prove the problems. So I've just taken an example with 0, 1 here, for B as 0, 2, 3 and C as 0, 4, 5. Then I've taken the A intersection B where the common elements for both A intersection B and A intersection C, and you can see that in these sets, for set B, 5 is not included, that is, so B is not equal to C. Again for the set A, set C 2 is not included, which is there in set B, and hence B is not equal to C. Now let's do the 11th problem. Let A and B be sets if A intersection is equal to B intersection is equal to 5 and A union X is equal to B union X for some set X. Show that A is equal to B. And there is also a hint given. A is equal to A intersection A union X and B is equal to B intersection B union X. Use distributive law. So let's consider here that there are two sets A and B, and it is said that A intersection B is A intersection X is equal to B intersection X, and A union X is equal to B union X for some set X. Right? And it is said that if we can represent it here, hint is given that A intersection A union X. It is true, right? Now let's use here A union X is same as what? A intersection B union X. We can write like this also, right? Because A union X is equal to B union X. Now let's apply here the distributive law. What is that? A intersection B union A intersection X. And in the problem it is said that A intersection X is equal to 5. Since A intersection X is equal to 5, you can say that A intersection B union of 5, which is equal to A intersection B. So we have proved the first one. Now let's take the B. What you will get for B, you can see. B is equal to B intersection B union X. Similarly, here you can substitute what? B intersection A union X. As I said, it is not mandatory to use the hint and find in this method itself. You are free to use your own ways. Yeah, you just have to prove that at the end A is equal to B. I'm just using this method. If you find it easy to follow, you can use this method and find the answer. So let's back into the problem. B intersection A union X. Again, using the distributive law, what happens? B intersection A or A intersection B union B intersection X. Again, you know that B intersection is equal to 4 phi, that is A intersection B union phi, that is equal to A intersection B. From both sides, we can compare and write that A is equal to B. This is one of the easiest method. That's what I have used. But as I said, you are free to use your own methods. Okay. To the 12th problem, find sets A, B and C such that A intersection B, B intersection C and A intersection C are non-empty sets, but A intersection B intersection C is equal to 5. So now I'm going to write an example in such a way that A intersection B and B intersection C and A intersection C are non-empty sets. But if you take the intersection of all these sets, it will be an empty set. It's very easy. You can take any example. As I said, I'm taking the example, let A is equal to 0, 1. B is equal to 1, 2, C is equal to 2, 0. So if you take A intersection B, what you will get? Set with element 1. Again, B intersection C, again it is a non-empty set, right? Again, B intersection C is 2. This is again a non-empty set. Again, A intersection C is again what? 0. So these are all non-empty sets. But again, now you can take that A intersection B intersection C. A intersection B intersection, are there any common elements? No. So it is an empty set, and hence you have proved it. That's it for the 12th problem. As I said, you can take any examples. I've taken with smaller examples, then you can find your answers very easily. So try to take with 2 or 3 elements in your problems, then you can easily find, or else you have to use more steps to find the answer for the problems. Now let's go to the 13th problem. Let's read the question. In a survey of 600 students in a school, 150 students are found to be taking tea and 225 taking coffee. 100 were taking both tea and coffee. Find how many students were taking neither tea nor coffee. UB here, the set of all students who are taking part in the survey. So let's consider that set, that is U is the universal set. Set of all students who are taking part in the survey. And let T be the students who are drinking or students taking tea. And C be the set of all students who are taking coffee. So it is said that N of U, that number of students are 600. Number of students who are taking coffee, it is N of C is 225. And it is also said that number of students who are taking tea, that is 150. Then what is it said? 100 were taking both tea and coffee, that is N of T intersection C, that is given as 100. So in our problem, we need to find how many students are taking neither tea. Neither tea means what? Like neither tea nor coffee. That is, students who are taking tea complement is the students who are not taking tea. And not coffee also. That means T intersection C complement. You can apply your De Morgan's law here. So what you will get here? T union C complement, right? What is that? That is N of U minus N of T union C. That is T union C. Again, you know that what are these? N of T plus N of C minus N of T intersection C. So substitute all these values and you can easily find your answer for this problem. So N of T union C, the whole complement is equal to 600 minus 150 plus 225 minus 275. So which will give you 325 students. So there are 325 students who are taking neither tea nor coffee. I hope it's clear. It is a very easy problem. You just have to find it difficult to get the answer. You can draw a Venn diagram and slowly analyze your problem. So now let's go to the 14th problem. If a group of students, 100 students know Hindi, 50 know English and 25 know both. Each of the students know either Hindi or English. How many students are there in the group? So again, let's consider n of u, that is u be the set of all students in the group, and e be the set of all students who know English. So e is the set of all students who know English. Again, h be the students or set of all students who know Hindi, and we know that h union e, that is equal to the universal set. That is the set of all students in the group. It is why, because it is said that students know either, but that is all the students in that either they know Hindi or English. So we can say that h union e is equal to the universal set. And what is n of h in the question here? N of h is given as 100. Again, n of e is given as 50. That is the number of students who know English. That is 50. Again, we need to find how many students are there in the group. And we know that number of students who know Hindi as 100 and English as 50. Now we have to find the h union e from it, right? So let's find it. N of h union e, that is n of h plus n of e minus n of h union e. So let's find that n of h is already given, that is 100. Again, e is also given, that is 50. N of h union e is also given, that is the 25 know both. The 25 students who know both, that is an intersection. Sorry, I have written wrong. H intersection, yeah. 50 minus 25, and that is 150 minus 25, that is 125. Hence, there are 125 students in the group. It's very easy, right? Now let's discuss the 15th problem. In a survey of 60 people, it was found that 25 people read newspaper H, 26 read newspaper T, 26 read newspaper I, 9 read both H and I, 11 read both H and T, 8 read both T and I, 3 read all 3 newspapers. Find the number of people who read at least one of the newspaper. So we have transformed our problem into 3 sets A and B, A, B and C. So let A be the set of all people who read newspaper H. Let B be the set of all people who read newspaper T. Let C be the number of people who read newspaper I. And from the problem, it is already said the number of people who read newspaper H, that is n of A, is equal to, already given in the problem, that is 25. Again, number of people who read paper T, that is also given, that is 26. N of C is also given, that is again 26. And intersection I, that is A intersection C, that is given as 9. N of A intersection B, that is people who read both H and newspaper H and T, that is also given, that is 11. And the people who read T and I, that is n of B intersection C, that is 8. And the number of people who read all the newspapers A intersection B intersection C, that is H, T and I, that is also given 3. So first problem is that we need to find the number of people who read at least one of the newspapers. From the practical problem sum sets, we have already learned to find the number of A union B union C, right? What is it? N of A plus N of B plus N of C minus N of A intersection B minus N of B intersection C minus N of C intersection A plus N of A intersection B intersection C, right? This we have also proved in the part 11. If you have any doubts on this formula, please refer on my part 11 where I have discussed in detail. And also quick reminder, if you wanted to learn on any other exercise on the chapter 1 sets, please have a look on my playlist on my channel. There you will see the complete list of videos on the chapter 1 sets. Now back into the problem, let's find the number of people who read at least one of the newspapers. That is the number of elements of A union B union C. That is 25 plus 26 plus 26 minus 11 minus 8 minus 9 plus 3, and that is 52. So 52 people read at least one of the newspapers. And now we have to find the second part, is that to find number of people who read only one newspaper, who read exactly one newspaper. That is either the newspaper H. Only H means what it would be? This region, right? Only T means what it would be? This region, right? And if it is only I, it would be this region. So these are the number of people who read exactly one newspaper. We need to find that. Okay. So we have, for our convenience, let's denote the B as the number of people who read I and H. Let C be the number of people who read T and I, and D be the number of people who read all three newspapers. A be the number of people who read H and T. So N of A intersection B you can write as A plus D. Again, N of B intersection C you can write as C plus D. Again, N of C intersection A you can write as B plus D. N of C intersection A is equal to B plus D, and N of A intersection B intersection C is what? It is also given, that is given as 3. If you subtract A, B and C and D from the set A, B and C, then you will get the number of people who read exactly one newspaper. That is, if you subtract from 52 the number of elements of A plus B plus C plus D, you will get the number of readers who read exactly one newspaper. We know that A plus D is what? A plus A intersection B. That is A intersection B, 11. And what is B intersection C? B intersection C is 8. Then again B plus D, that is C intersection A. A intersection C, that is given as 9. So 52 minus 11 plus 8 plus 9 minus 2D. Because in each of these you can see that 3 D's are added, but if for our problem we have only 1 D. So I have subtracted 1 minus 2D. And so you will get in the end 52 minus 22, that is equal to 30. So there are 30 people who read exactly one newspaper. So if you have any confusion in the future also, try to remember that, draw the set for each of these configuration. Then you have to always start from the intersection, the total integration, that is A intersection B intersection C, you have to mark. Then if you wanted to find the A intersection B only of these three sets, then from that you will get A plus D is the A intersection B. Similarly, D plus C is the B intersection C. A intersection C is again B plus D. So if you have to find the B, you have to subtract from B plus D, D to get the only the elements which are here. Yeah, I hope it's clear. This is very easy. Just try to draw with the Venn diagrams. The 16th problem is, in a survey, it was found that 21 people liked product A, 26 people liked product B, and 29 liked product C. If 14 people like product A and B, 12 people like product C and A, 14 people like product B and C, and 8 like all three products, find how many people like product C. As I said, when a question like this comes, you have to always mark which is common for all three sets. That is 8 like all three products. You have to write 8 here. Then what it is said? 14 people like product A and B. A and B means this is the section, right? If you take two sets, A and B, this section is also a part of C, right? This is a common section and it is already said as 8. And it is said 14 people like both A and B means 8 plus this region, that is 8 plus 6. That is here what marked as 6. Again, 12 people like product C and A. 12 people like product C and A. That is 8 is so common. Again, from that 12 minus 8, that is what written here as 4. Again, 14 people like product B and C. 8 is common for liked by all that is like 8 people like all these 3 products, and 14 like both B and C. From that, so you have to do 14 minus 8, that is 6, that is C. Now we have to find the number of people who like product C only, that is this region, right? People who like only product C, and that is the elements which belongs to C, and elements does not belongs to A, X does not belongs to B also. So we have to find only the elements which have thus only belongs to the products P. So we have to find number of people who like only products C. 29 people like product C. Out of that, we have to find the number of people who like only C. Means what you have to do? You have to minus from 29 all these intersections, that is 4 plus 8 plus 6, that is 29 minus 18, and your value is 11. So the 11 you can write here. So 11 people like both, 11 people like product C only. I hope it's clear. It's very easy problem. You just have to start with a Venn diagram. Then you have to start always from the intersection. That is a common region for all the 3 sets. That is the inner subset. Then you have to start with the smaller subset regions. Then you have to mark the only for sets A, only for sets B, and only for set C. From that, you can easily find the answer and find the solution. So that's all for the chapter sets exercises problems. And on my next video, we will do the further work problems based on the chapter 2 relations and functions. Bye bye, and I wish you all a nice day.